I'm Dr. Shweta Dalal. I'm a postdoc at the University of Exeter. So far you've heard a lot about exoplanet atmosphere. I'm going to talk mostly about how they orbit these stars. Now, I will be talking mostly about this HT 3167 planetary system, which I studied during my PhD. So before we go into the details about HT 3167, I would like to take you back to our solar system. As you can see that all the 8 planets are in this same plane, roughly in the same plane around the sun, with its equator and rotating around its equator. But do all the planets look like that? We know that's not the case today, and I will take you to this system which is quite different from our own solar system. So here you have a star which is smaller and less massive than our own sun, and it has 4 planets around it. During my PhD, I looked at one of these planets and found that it was in polar orbit around the star. What it means is that it orbits the star across its poles rather than going around its equator. Now, how do we find that? So we've heard in previous talks that when you look at the transiting planet, you look at the brightness dip in the brightness of the star when the planet comes across it. But remember that the star is also rotating. So the part of the star which is coming towards us is going to have light slightly blue shifted, and the part of the star which is going away from us will have the light slightly red shifted. So imagine if a planet was going across the equator, it will first block the light which is blue shifted and then block the light which is red shifted. But if it's a polar planet, you'll see either it will block the blue side of the star or it will block the red side of the star. So this is how we can find how a planet is orbiting around its star. Now, as I mentioned that for HT 3167, we found it to be in a polar orbit as it was only blocking the blue side of the star. Now, why is it so interesting? As you heard in Seb's talk, that all the planets form within the disk, so they are supposed to be aligned in the same plane. But in this case, you find it slightly different. So it challenges our planet formation theories. Also, it raises more questions like how did this planet end up in such a strange orbit? Did it get tilted by some external force like a passing by star? Or something happened to the star itself which changed its spin axis. So the discovery of a polar planet actually helps us understand more about the planet formation, how they evolve. So thank you. Yeah? Yeah? Thank you.
Great. Which way do we go? Wait, how does it work? There we go. Thank you very much. Like that? Is that okay? Yep. They're good? Thank you very much. Cool. Oh, you got the clicker? Which button is it? Just right in there. Cool. Okay. So just switch. Sweet. Thank you. Cool. Good to go? Hey, what's up, guys? Thank you very much for joining us today. My name is Matt Lodge. I'm here from the University of Bristol, and I want to tell you a little about what we're studying in terms of aerosols, little solid particles that exist in other planets in completely different solar systems to ours. So the context is we're looking at these planets that are orbiting stars, and our only way to access information in them is by looking at the light that either bounces off the planet or travels through the atmosphere of the planet as it passes in front of the star. So when that happens, there's a couple of things that we expect to find in the atmosphere. One of those things is clouds, and if you look behind you, there's clouds up there today which are a very different color to the rest of the sky. And what that's telling you is that clouds interact differently with light to the rest of the gases in our atmosphere. So these clouds we expect to find on exoplanets as well. At various heights, we can actually figure out, based on the amount of gravity on the planet, where we expect to find them height-wise, what they're made of, these amazing exotic chemicals. So if you remember the periodic table, we've literally got that entire chemistry set to use your imagination and play with on these amazing new worlds that have a variety of properties. You might also remember a couple of weeks ago that on the east coast of America, it was entirely covered in this haze. And so this haze is basically formed of particles that are less than 1,000th of a millimeter across. And these tiny, tiny particles can also really, really change the light that passes through the atmosphere. So we get this kind of massive orange absorptive glow, which is blocking your view. And the same thing can happen on exoplanets as well. And so my research primarily is dedicated to how do these little bits of dust affect the light that goes through them. And we can start by a really, really simple model where we say, okay, let's pretend they're spherical. How would that little sphere affect light? And even that problem has these amazing weird consequences. So if you imagine it's a really, really sunny day and you open a parasol on the beach, it'll make a shadow. What's really, really weird about these particles is that they actually absorb way more light than their size. And so that's like you opening this parasol and suddenly the entire beach becoming black, right? It doesn't really make sense just to thinking about it. But if you do the maths and you study this in detail, these particles can absorb way, way, way more light than you would think. So it's a complex problem, and that's just when we have a really simple model and we're pretending the particles are spherical. But in reality, they're actually much, much more complex shapes. So in reality, they look a little bit more like this. So instead of a sphere, we have these wonderfully complicated shapes, and suddenly the mathematics of trying to work out how this particle is going to scatter light becomes really, really challenging. Oh, thank you. And so that's primarily what our research is dedicated to doing, finding out how these particles scatter light so that we can better understand exactly what's in the atmosphere of these amazing new worlds. Thank you very much. Cheers. Thank you.
Thank you very much. Come on up. I thought you might need it.
Okay. And you? Hello, good afternoon. Can you hear me? Yeah, cool. Cool, let's talk about the sun. So this is a picture of the sun, and it was taken, every different colour here is a different wavelength of light. So going around for the green here, this is X-ray light, all the way through different colours of the ultraviolet into the optical light that we can see. And all these images are taken at the same time. So this is what the sun is doing at all these wavelengths at the same time. And you can see it's completely different. So what we see down in the X-ray, there's completely different structures, completely different activity, and completely different layers of the sun that we're seeing as we go down to what we can see with our eyes. And each of these layers, each of these wavelengths of light has a different effect on the Earth. The X-ray light can strip away our atmosphere, the UV light will change the chemistry of the atmosphere, the normal light, optical light, heats up and gives us the heat we have. And we want to know this for other stars and other planets, except it's very difficult to do with our current set of observatories. So we have observatories that can see in different lights and different, say, X-ray light and UV light, but getting them all to work together is really hard. It's not impossible, and actually at 6 o'clock this evening, the Hubble Space Telescope will be observing a star for me, so look up and hope that works. But getting them all to coordinate, getting all this light at the same time is really, really hard. So we need another way of doing it if we want to understand the stars that all these planets that we're discovering are orbiting around. So we looked at biology instead. So anyone know what this is? Mantis shrimp, yes. So mantis shrimp, they are about this big, they are really cool, but they have perhaps the most complex eyes in the world. Whereas we can see in 3 colours, mantis shrimp can see in 12 to 16 colours, depending on species. So we took inspiration from this and said, okay, why don't we build a telescope that can see in all these colours at the same time? So this is Mantis. This is our telescope that we are building at the University of Colorado. We'll be launching in 3 years' time, and we'll be observing in all these different wave bands of ultraviolet light into X-ray light, all at the same time, looking at these stars that have planets around them, looking at the light that comes from the stars and how that light affects the planets. And it is going to be the most advanced astrophysics CubeSat ever built, and we are very, very pleased, especially with the extreme ultraviolet light. This will be the first extreme ultraviolet mission for 20 years. And the last thing that we've taken inspiration from the mantis shrimp is the size of our CubeSat. Our space telescope here, instead of those giant things like Hubble and JWST, this will be about 30 centimeters long. So thank you very much.
Thank you. Okay, so that one is to click on this one.
Like this? Great. Thank you. Hello, my name is Evelyn MacDonald. I am a PhD student at the University of Toronto in Canada, and I study the climates of tidally locked planets. So let me just kind of walk you through what that means. The best analogy I can think of is when we look up at the moon, you may have noticed, we always see the man in the moon, which means that we're always seeing the same side of the moon. That's because the moon is tidally locked to Earth, which is what you can see here. Basically, the same side of the moon points at the Earth all the time as it rotates around our planet. So the moon is tidally locked to us. Now, the Earth rotates around the sun, and we have a day-night cycle, but some planets, much like the moon with the Earth, are tidally locked to their stars. So here you can see what that looks like. We have a redder star, so a smaller star, and a planet orbiting around it. And the same side of the planet always points toward the star as it rotates around. So consequently, that side is very hot. It's called the day side. And the night side, away from the star, never gets any direct radiation, so it's very cold. So I'm sure you can imagine it's a very different climate to what we're used to on Earth, because there's no seasons, no day-night cycle, always just hot and cold. So in my research, I look at what happens on the hot side of the planet if we change what the surface looks like. So we can put land, or we can put ocean in the middle of the day side, and then there's ice everywhere else, or there's land everywhere else, but we can't have ocean on the cold parts of the planet because it'll just freeze into ice. So you can imagine that the planet would have a lot more water in its atmosphere if it has a big ocean in the middle of its day side. So in my work, I use simulations to understand whether these planets could maybe host life. And we find that when there's a lot of land in the middle of the day side, our planets have very hot, dry deserts. But if we move the land a little bit away, we get instead a nice oasis with lots of rain and lots of clouds and a much more even, temperate climate. So these planets could maybe host life, but we need to think about which side is pointing toward the star to think about where the aliens might like to live. Thank you very much.
And Sasha Hinckley, our final speaker. So that needs to be kept on now.
Where's this go? You should be. Talk into here? Both. Hey everybody, I'm Sasha Hinckley. I'm an associate professor here at the University of Exeter. I'm going to tell you just briefly about how we are directly imaging extrasolar planets around nearby stars using predominantly the James Webb Space Telescope. So you've probably heard about a lot of exoplanets so far, but actually we can take pictures of these exoplanets as they orbit their star. Most of the exoplanets you've probably heard about were only discovered through indirect means, where we basically infer the presence of an exoplanet due to some effect it has on its host star. But now we can actually take images of extrasolar planets, and sometimes even as they orbit around their host star. And this is an incredibly challenging technical achievement to do this. And to give you a sense of that, we could think about two of the separations, two of the challenges that we face. The first challenge is the separation on the sky, actually how close this planet is on the sky from its host star. So here's just a little graphic showing an illustration of what an orbit of a Jupiter and an Earth might look like if they were orbiting around this nearby star. Now this big white sphere here is not actually the star itself, that's just the really, really bright glare from the star itself. The actual star itself would be about the size of a little speck of dust on this screen, much, much smaller than this. But all of this huge glare is something that we need to cancel out. And we do that using some technical things in both hardware and software. And typically these angles on the sky are very, very tiny. This is 1 arc second. And if you're not familiar with what an arc second is about the size of a 1-pound coin from 5 kilometers. So this is the patch of sky that we do our science on. To give you a sense of the other challenge that we face, you can think about the brightness difference between a very, very faint planet and a very, very bright star. And it turns out that the brightness difference is very, very similar to basically a firefly compared to a very, very bright searchlight. So you can imagine trying to take a picture of a firefly as it walks around the edge of this searchlight. Now imagine trying to do that from Exeter, but if you put the searchlight in Bristol. So imagine trying to do that, and that's really the challenge that we're trying to do here in this field of extrasolar planet direct imaging. The instrument that we're really using a lot to do this is the James Webb Space Telescope, which has been an amazing technological achievement for actually doing this. And recently we were actually able to uncover the first ever direct images of an extrasolar planet using the James Webb Space Telescope with the help of people like Shrishmoy Ray here at University of Exeter that you might have heard from earlier, and Aaron Carter, who was a former PhD student here. So here we have an image of a nearby star, and we were actually able to take an image of a planet in several different wavelengths, and this is allowing us to see planets in totally new wavelengths. It's going to allow us to do a huge host of science to understand things about their atmospheric compositions and maybe even clues to their formation. So I will end there and hand it back to Natalie.
We have one more speaker for you, Professor Nathan Main, who's been organising the entire conference and who's a fantastic speaker. You have to look him up. We do a lot of work with him and he's fantastic. So Nathan, I know you're tired. Just a little bit of a chat from you would be wonderful. I'm going to clip this.
No worries. Perfect, thank you. So thank you to everyone that's taken the time to stop and listen today, and also if you've joined us online. We've had this conference in a summer school in Exeter for the last 10 days. I live and I work here, and I grew up in the southwest, and sometimes you go about your daily business and you perhaps don't realise the kind of cool stuff that's going on just up the hill in the university. So for people, especially maybe young people at the college, or if you're watching this online and you're at school, these kind of careers, this kind of exciting stuff, you can all do it if you want to. People spend a lot of time telling you what you can and you can't do and what you're good at. The truth is they don't really know, so just find something that you're passionate about and go for it. Thank you very much.
So thank you all so much for joining us today. If you missed any of those talks, do have a look on our YouTube channel. The whole set of talks will be on there, and you can catch up. There's more information, there are more resources, and also we're going to have a fantastic, if I don't say so myself, exhibition coming up for the British Science Festival, which is coming to Exeter this year in September. Will be open from the 6th to the 10th of September in Make Tank on Paris Street. So if you enjoyed this, come along, chat to the astrophysicists, have a go on our VR headsets, and play with some cool demonstrations. That's September. If you want to find out more, scan one of the QR codes on one of the signs you can see there. We've also got some nice flyers that we can hand out. Stay in touch, look us up, Exeter Science Centre, and thank you so much for taking part. Hope you've enjoyed it, and thank you so much to our amazing set of speakers. You've been wonderful. Thank you.